go from this version to the more generalized version. And what I'm actually going to do is I'm going to change this slightly. So let's make this a squared using this rule. So what we want to do is we want to transform this equation into something like that. And the way you would do that is you have to multiply by and divide by the same quantity. So what I would do is I would take this and I would multiply by 3 and divide by 1/3 first. So I can take this 1/3 inside the square root, but because you're going in the square root, you square it. Why am I doing 3? I should be doing a, sorry. It's because that's what it was before. So I'm going to multiply by a and divide by a. So we're going to take this and move that inside the square root. So we'll have 1 over a times the square root of a squared divided by a squared minus x squared divided by a squared times dx. And then we're going to use this u substitution that u is equal to x divided by a. So du is going to be equal to 1 over a times dx. So that goes to 1. So you get 1 over a, and then you multiply it by dx. So with that substitution, we can write this, and I'm going to factor the 1 over a outside the integral. So what I'll end up with is 1 divided by the square root of 1 minus u squared times du divided by a. If I solve for du, well, actually, no, yes, no, it's times a, sorry. Let's go back here. So if what I'm substituting here is for dx, so I have to solve for dx. So dx is equal to a times du. So for dx, I'll put in a times du. This is 1. This is x over a, which is u. So that's u squared. So I get a times du. And then I can factor the a out again. So I'll get a over a times the integral of 1 over the square root of 1 minus u squared times du. And the integral of that is just going to be equal to the arc sine of u plus c and then u is equal to x over a plus c. So that was originally that was equal to, let's go back over here. So that's equal to this, but it's also equal to that. So let me make sure I get this right here. So that's that. I'm missing something, so I'm trying to figure out where I went wrong here. So 1 over the square root of a squared minus u squared du is equal to that. And I should have a 1 over a, so what did I mess up here? Okay, so I'm starting with that. Multiplying, dividing by a. Oh, no, it is right. I was thinking this one. There is no 1 over a. Okay, so I did do it right. I just didn't remember the right. So this is the formula that we're using. The integral of d over the square root of a squared minus u squared equals the arc sine of u over a plus c. So that's what I ended up with. So it is right. When you do that with the arctangent version, to generalize it, you get a 1 over a in front, but with the arc sine, you don't get 1 over a. You just get the arc sine of x over a. So that's where that comes from, is you just do a little dividing and multiplying by the same constant. Okay. So those are the 3 formulas. And so let's just do a few examples that are they're u substitutions, but they're not super difficult u substitutions. So the reason we would not, normally up to this point we would have thought that u is equal to 25 minus x to the 4th. But if we take du, we end up with negative 4x cubed dx, which we don't have here. We have just x dx. So we're going, that's not going to work. Sometimes you just try things because that's what you've done in the past. So the only other similar form to this equation we have is where this would be u squared and this would be a squared. So in these problems we have both u and a. So what we're going to do is we're going to say u squared is equal to x to the 4th and a squared equals 25. So you take the square root of that and you'll get u is x squared. So u squared is this term, the whole term. Then you take the square root to get u. And that's because the final answer is in terms of u. So we want to do this, find out what u is. Then you would take the derivative of u. So du is going to be 2x times dx. And you can see that we have x dx here. So that matches up with what we had there. When we had it this way, we had x cubed, which wasn't in the original equation. So that looks like it's going to work much better. If a squared is 25, then a is 5. So the substitution, what we're going to do here is we're going to solve this for x dx. So x dx is equal to du divided by 2. So we'll use this substitution here for those two. A squared is 25 is that part, and u squared is x to the 4th. So if we make those substitutions into our original equation, x dx becomes du divided by 2. This part is just 1 over the if I group these together, this is 1 over the square root of 25. So I end up with 1 over the square root of a squared minus u squared. So I factor out the half. So I get the integral of 1 over the square root of a squared minus u squared du. And again, the whole purpose of this u substitution is to take the original equation, which we don't have a formula for in the book, and to convert it into something exactly equal to what's in the book, which I have now done. If you look in the book, you'll see that the integral of 1 over the square root of a squared minus u squared du is equal to the arc sine of u over a. So now I can use my formula to then do the integration. So I'll get 1/2 times the arc sine of u over a plus c. And then I go back and do the substitution. So I substitute both u and a. Even though the original equation had a squared and u squared, the solution has u and a. So I end up with 1/2 the arc sine of x squared over 5 plus c. And that's your answer. Okay. So let's see what's on the next page. Oh, this is just to remind us these are some of the things we don't know yet, but we will know in chapter 8. So we don't know what the integral of the arc sine is. We know what the derivative of the arc sine is, but we don't know what the integral is. We know what the derivative of the natural log is, but we don't know what the integral of the natural log is. And if I switch a squared and u squared, so it's u squared minus a squared. I don't know how to do that either yet. Okay, so small changes seem like small changes. All I'm doing is changing the order. Here, it seems like the natural log's not that hard a function, but at this point we don't know the answer. We don't know how to do it. Okay, so there are 4 different techniques we're going to look at for doing problems like the one I just did. They're a little more complicated. We did integration by substitution, so we'll do a few more of those. Sometimes rewriting the quotient, the original quotient, as a sum of 2 quotients. Sometimes completing the square to get it into this form of the integral of 1 over the square root of a squared minus u squared. It may not look like that initially, but we can make it look like that by doing some things. And also completing the square where you have a negative leading coefficient. What that means is, well, I'll show you when we get to it. Okay. So here's some integration by substitution kind of problems. So what you do is you look at the original equation and say, is there a choice of u and a which can make it so that I can rewrite that equation after factoring out some constants to make it look exactly like the formula that we have. So hopefully you would say, well, it looks like a should be 1 because a squared is 1. And we're subtracting u, so u squared should be the second part. If u squared is x squared, then u is going to be 2x. So I'm going to let you do the rest of the problem. So we're going to say a squared equals 1, u squared equals 4x squared. So what you'll do is you figure out what a is, you figure out what u is, you'll figure out what du is, then you'll make the substitutions into here. If there's some constants you need to deal with them, factor them out, get the equation exactly like this based on these substitutions with the constants out front, and then just use the formula using the u value that you've gotten here and the a value that you've gotten there. So when you have something, a constant times something, you take the square root, all you do is take the square root of the constant part. So that's going to be 2. And you take the square root of this part, square root of x squared is just x. By the way, you guys who missed the physics test on Friday, y'all get zeros. No, just kidding. You can take tomorrow in study session. Yes.
I have a mandatory choir thing on Tuesday.
Oh, do you?
For the Association of Retired Teachers.
Oh yeah, yes, yeah. The usual. Yeah, I remember they do that every year.
Yeah, I'll have to leave physics about like 9:50.
Okay. So what I'll do is I'll let you take it during calculus. So I'll just give it to you, and you can. So we'll do that. I still want you to take it tomorrow. Yeah, I got to about problem 4 on Friday. Yeah, I was tired. Okay, so the answer is 3/2 the arcsine of 2x plus c. So I factored out the 3, then I made the substitutions. Well, actually, I factored out 3 and made the substitutions. So we ended up with du over 2 for the substitution for dx. So then I factored out the 2 as well in the denominator. And then I'm like, yay, I got it. I got matched the one exactly. So then all I have to do is write out the formula, make the substitution back in, simplify it. Okay, let's see what we got next here. Okay, so this is let me find the equation so you can see what the equation is. Well, I'll write it out for you. So hopefully you would say, oh, this kind of looks like this 1 over a squared plus u squared du formula. That's the 1 over a times the arc tangent of u over a plus c. So that's the formula we're trying to fit it into, and it's because we don't have a square root, and we're adding the stuff together. So it fits, in general form, it fits what we have, but we just need to, again, let me just move these two so you can start off. The key thing here is, you've got to determine what a squared is, then you can find a, u squared, then you can find u, du, make the substitution so that this, with the proper choice of a and u, you end up with this, and then you apply the formula and get the answer. So these are easy. There's at least one of these easy ones on the test. Yeah, it's only a week till our exam, isn't it? Wow. There's your answer. 7/4 times the arctangent of x over 4 plus c. So when you have just x squared as the u squared part, the du just simply is dx. There's no factor in there that you have to worry about. If a squared is not a perfect square, it's no big deal. A would just be the square root of whatever that number is. So we'll do one that doesn't we just do a perfect square because it looks nicer. You don't have to deal with the square roots, but they're not that big a deal. Okay, so those are the easy ones. Okay, so let's move on to the next. We're going to skip that one for right now. We'll let you practice some tomorrow, but these are all basically the same kind of things. Okay. So the next one is completing the square. So a lot of times, sometimes you have ones that don't immediately lend themselves to having part of it being a squared and part of it being u squared. So what we have in the denominator is a second order polynomial, quadratic. And again, you might think, well, maybe this is going to be the natural log, because if I let the entire denominator be u, if the numerator was du, then it would work out perfectly, but it doesn't, because if I take the derivative of x squared plus 8x plus 20, I'll get 2x plus 8, and there's no 2x plus 8. There's no x in the numerator. So that kind of rules out doing that. So then we try to make it fit into one of the three formulas that we have. 1 over the square root of a squared minus u squared, 1 over a squared plus u squared, or 1 over u times the square root of u squared minus a squared. Those are the three that we know at this point. So because there's no square root, it has to fit the arctangent form. What we're trying to do is we're trying to fit it into this 1 over a squared plus u squared du equals 1 over a times the arctangent of x, or u over a. Okay, so that doesn't look like that. But if we complete the square on the denominator, so we take the denominator, and what we'll do is we'll first, this is not really doing anything mathematically, it's more cosmetic, is I'm going to put the constant term to the right. So there's a space in there. And completing the square just means that we want to take the two parts of the quadratic expression that involve x squared and x and add a number such that I can make those three numbers into a perfect square. So it's a factor, something x plus or minus something squared. So the way you do that is you take this coefficient, 8, you divide by 2, and you square it. So that's 4 squared, which is 16. So what I do is I add 16 and I subtract 16. Because I don't want to change the value of this expression at all. All I want to do is just change the way it looks. But if I add and subtract the same thing, that's algebra. Things are unchanged. Now, this, because of the procedure I used, I can always collapse this into x plus or minus something, and the thing used, the factor that goes with x is this number. Whatever you have, 8 divided by 2. If it's negative 8 divided by 2, it means negative 4. So it's plus 4, and then you square the whole thing. And you can see that if I use FOIL to evaluate this, I'll get, if I take x plus 4 times x plus 4, that's x squared plus 4x plus 4x plus 16, which is going to be x squared plus 8x plus 16, which is what I had here. So I'm going kind of the opposite direction. Instead of going this way, I'm going that way. So I can replace that with that, and then I do the math here, so that would be plus 4. So before I try to use any u substitution, I'm going to use completing the square. First thing, I'm also going to factor out the 13 because that's usually not something that I need right now. And then I can replace the denominator with x plus 4 quantity squared plus 4 times dx. Now I look at this and I say, okay, well, the part that involves the variable is the u part, and the part that involves the constant by itself is the a part. So I could rewrite it, I don't have to rewrite it, but let me just change the order of the denominator so it's 4 plus x plus 4 quantity squared dx. So at this point I can make some decisions. I can say a squared equals 4 and u squared is equal to x plus 4 squared. And therefore a is equal to 2 and u is equal to x plus 4. And then I can take du, which is just dx. Derivative of x is 1. The derivative of 4 is 0. So I just end up with 1 when I take the derivative of x plus 4, and then I multiply 1 by dx to get dx. So with those choices for u and for a, I can now take the original expression here and make my substitution. So I end up with 13 times the integral of 1 over a squared plus u squared times du. And there I am. See, I'm back wherever I was earlier. I was trying to get this to look like that, which I did. So at this point, I just look up the formula. It says it's 1 over a times the arctangent of u over a plus c. And then I plug in a and u. So I get 13 over u is a is 2, so I get 13 halves, times the arctangent of u, which is x plus 4, divided by a, which is 2, plus c. And that's your answer. So how would you know how to do this? Well, the first thing you do is you think the entire denominator would be u. You always want to try the natural log as a solution. But we found out that the derivative of this thing when it was multiplied out wasn't anything close to the numerator. So then we say, okay, plan B. Plan B is, well, does it look like any of the 3 arctangent or arc-trig functions? And you're like, oh yeah, there's something about, I've got a squared term. Maybe if I use completing the square, I can rewrite the denominator to fit the requirement wherever it's on the previous page. And so by completing the square and then choosing a and u appropriately, then you can get it into an exact form that's in your book. Then you can just use the formula and then substitute back in. So, okay, so let's look at another one. Maybe you guys can do this one. Okay, now this one's a little different because it's got, this is where you have a square root of something. So it has to end up being the square root of a squared minus u squared. And people mess this up, so I'm not going to leave it up to you right now. You'll get to practice later. So I have to use completing the square. Just like here, I took this entire denominator and used completing the square to rewrite it. I have to do the same thing here. So I'm going to take 20 minus 4x minus x squared. And what I'm trying to do is get a squared minus u squared. That's the idea. So the way I do this is I take the constant just like I did in the previous problem, and I factor out the negative sign. So if I factor out the negative sign for these two terms, I'll have 4x plus x squared. So negative 1 factored out gives me that. And then I would change the order just because it fits with what I had before. So I'll have negative the quantity x squared plus 4x. And I'm going to leave a little space in there because now I'm going to complete the square here inside the parentheses. So I take this term, the coefficient in front of the x term, I divide by 2, and I square it. That's going to be 2 squared, which is 4. So I add 4 here inside the parentheses. But really, as far as the equation is concerned, I'm subtracting 4. So I'm adding 4 in the parentheses, but the sign change means that I'm subtracting 4. So I really have to add 4 to the whole thing. So let me just move this down a little bit. So, oops. Okay. There we go. So I've subtracted 4, so I have to add 4 back in. So I've got 20 minus the quantity x squared plus 4x plus 4. I add another 4 to make this work out even. Okay, so the next thing I'll do is I will add the two constants together. So I'll get 24 minus the quantity x plus 2 quantity squared. And again, it's this number here that is this number there. So does that look anything like a squared minus u squared? Yeah, if a squared is 24 and u squared is x plus 2. So that's having completed the square. But before I do that, I'm going to rewrite the original expression. I'm going to factor out the 8. So I'll have 8 times the integral of 1 over the square root of this thing that I got down here, 24 minus the quantity x plus 2 squared times dx. So again, I haven't done any u substitution up to this point. I've just used completing the square. It's a little more difficult when you have a negative coefficient in front of x squared, but not that much more. You just have to take into account when you add it, you're really subtracting it. Okay, so now we can choose a squared and u squared. So a squared equals 24, and u squared is equal to x plus 2 quantity squared. So a is equal to the square root of 24, and u is equal to x plus 2, and therefore du again is dx. So making those substitutions in, you get 8 times the integral of 1 over the square root of a squared minus u squared times du. And that was the whole goal, was to get it exactly like the book. So once you have it exactly like the book, don't leave any constants inside, then you can say, okay, I can just use the formula. So the formula that goes along with that would say I have 8 times the arc sine of u over a plus c. So the result of that integral is this antiderivative. And then finally you plug in u, which is x plus 2, divided by a, which is the square root of 24. And you could simply, if you got this far, you're right. I'm not going to mark you wrong. To be mathematically correct, you would multiply and divide by the square root of 24, so you get the square root of 24 times x plus 2 divided by 24. So multiplying by the square root of 24 by the square root of 24 gives you 24. And then you could also rewrite this as 2 times the square root of 6. So you can, factoring out the square root of 4 is 2. So you get 2 times the square root of 6 times x plus 2 over 24 plus c, and then you could simplify here. So you'd end up with 8 times the arc sine of the square root of 6 times x plus 2 over 12. and that would be your best answer. And that's a 2, not a C. So that's completing the square. So like I said, we'll practice doing both where you have, like for example, the arctangent, they're all positive, so that's easy. If you're involving the arc sine, you're always going to have a negative. You're always going to have to do a negative sign here. Okay, rewriting is the sum of two quotients. That's the next technique. So again, looking at it initially, you might say, let's try the natural log. And so you take you let in your mind, you'd say, okay, let u equal x squared plus 1. And when you do that, you get 2x. Well, I have x, but I also have that negative 3 that's kind of there to mess things up. So it doesn't work directly. And again, it also doesn't look like the arctangent because it's not, you've got the x in the numerator. So in one case, the constant messes it up. In the other case, for the natural log, if it was just x over the square root of x squared plus 1, it would involve the natural log. If it was just 3 over the square root of x squared plus 1, then I could use the arctangent. Well, what I can do is just make this into two quotients instead of one quotient by dividing each term in the numerator by the same denominator. So what I would do is I'd rewrite this as x, the integral of x divided by x squared plus 1 dx, and then I'd have minus the integral of 3 over x squared plus 1 dx. So this part, I would choose u as x squared plus 1, and here, and that's because if I take the derivative, I'll get 2x dx, which matches up well with this, except for this constant, which we can handle. In the second case, this looks like the arctangent thing, so I'd say u squared is equal to x squared, and a squared is equal to 1. U is equal to x, a is equal to 1, and dx is equal to du. So I have to use, different choices for u depending upon what the original, the two parts look like. So go ahead and finish that off. This one, you'll use the integral, and I'll write the two formulas down that you'd have in your book, and you can. So for the left-hand side, the formula would be that the integral of 1 over u du is equal to the natural log of the absolute value of u plus c, and the one on the right would be the integral of 1 over a squared plus u squared du is equal to 1 over a times the arc tangent of u over a plus c. So those are the two formulas we're going to fit it into. Okay, so there we go. You get 1/2 the natural log of the absolute value of x squared plus 1 minus 3 times the arctangent of x plus c. You know, if this had been x squared plus 9, the only difference is we'd have x squared plus 9 here, and you'd also have a would be 3 instead of 1. So it's not that much more difficult otherwise. Okay, so that's how that works. So I'm going to start this one. I'm not going to get it finished today. So this is reasonably complicated, but it puts together all that we were doing. Again, if you took the derivative of the denominator, you would get 2x plus 6. And I don't have 2x plus 6 in the numerator. I have x plus 5. But I could still break it into two quotients. I could have x divided by x squared plus 6x plus 22. The problem is, though, the derivative of x squared plus 6x is 2x plus 6, and if I just separate it into two quotients, it still won't work out. So what I need to do, what you need to do is come up with something that looks kind of like this. You need some constant a times 2x plus 6 divided by x squared plus 6x plus 22. And then you need another integral that's some constant b divided by x squared plus 6x plus 22. And these both times dx. The previous problem was easy because it just had x squared plus 1. Here we have x squared plus something x plus some constant. So to be able to use the natural log, substitute, the integral of 1 over u du, the numerator has to be equal to some multiple of the derivative of this. So the derivative of this is 2x plus 6. So it has to be some multiple of it. And this one just needs some constant. It doesn't matter what the constant is. As long as I can rewrite this, completing the square, so that I can get it into a squared plus u squared. So the first thing you do in these more complicated problems is you figure out how to break this thing up appropriately. And so all we have to do is we just have to take we have to figure out what a and b are. So we have a times 2x plus 6 plus b. That's where we want to get to, and write down where we start with on the right-hand side. So this is what we have. This is where we want to get to. So what are a and b to make this happen? Well, if we multiply it out, you'll get 2ax plus 6a plus b is equal to x plus 5. And we'll do this a lot more in other cases, is you take the coefficients associated with the x parts and you set them equal to the coefficients on both sides. So you actually, from this one equation, you come out with two equations. One equation is that 2a, the coefficient in front of x here, has to be equal to the coefficient in front of x on the other side. So that's the x parts. And then you take the constant parts. So the constant parts are 6a. On the left-hand side, the constants are 6a plus b, and on the right-hand side, it's 5. So you can see I have two equations and two unknowns from this one equation involving x's and constants. So here I can say a is a half, and then I can substitute that in here. So I'll get 6 times a half plus b equals 5. 6 times a half is 3. Subtract 3 from both sides and you get b equals 2. So what that means is that this original integral x plus 5 divided by x squared plus 6x plus 22 dx can be rewritten as this integral. So a is a half, so there'll be a half times 2x plus 6 divided by x squared plus 6x plus 22 times dx. That's the first term. Plus b, which is 2, divided by x squared plus 6x plus 22 times dx. Sorry, I ran out of space there. So all I've done so far, I've just used algebra to break the original quotient into two quotients, where one of the quotients, the numerator, is some constant times the derivative of the denominator, and the other one is just some constant divided by the denominator. So this one is almost ready to go, because if you let this be u, then this is du. Okay? 2x plus 6 times dx is going to be du. So that one's we've got far enough. The second part, we have to apply completing the square, because we need to get it fit into the integral of 1 over a squared plus u squared. And that's what we'll do next time. But I'm going to assign you the homework from this section, because I don't think I have yet. Did I do that already? I can't remember. If not, I'm going to do it now. Oh, there we go. Okay, so there's section 7. So that's it for today. Yes. Yeah, that's a good question. Thursday. Yeah, because it's.
You said that last class on Friday.
Did I?
Yeah. But isn't the test on Thursday?
Test is on Thursday, so I have to.
We still do it by Thursday.
Pardon me?
We still do it by Thursday.
Yeah, because otherwise you won't have done the homework before the test. So. Yeah, I thought I assigned it already, but it's due Thursday, because you'll have something on the test. So. You got 2 study sessions to, well, 1 study session to work on.